I'm here to present our paper, Finding Specification Blind Spots via Fast Testing. My name is Ru, and this is a joint work with my advisor, Professor Xu, and we are from the University of Waterloo. So let's start with some brief introduction of form verification. Form verification is an approach that delivers high assurance to systems by mathematically checking the correctness of a program. And compared with traditional testing approaches, form verification is usually considered to be able to provide higher assurance, but at the same time, it also requires higher cost. Typical application scenarios of form verification including cases where errors will lead to significant losses, for example, in the field of aviation, and cases where traditional routing upgrade model is not feasible, like in the case of smart contracts. And in recent years, we have seen many implementation of form verification, including SEL4 for operating systems, Raspberry for compiler design. And for the two case studies we used in this work, we have S2N TLS, which is the lightweight TLS protocol implementation developed by AWS, and Diem Payment Network, which is the blockchain-based payment banking system developed by Meta. So when we are applying form verification to a system, the process can usually be decomposed to two steps. The first one is to develop a complete set of specification for the target system. And the second step is to prove or disapprove that the actual implementation is in conformance with the specification. So since form verification is a kind of expensive approach, we definitely want higher assurance from it. But speaking of assurance, comparatively, the second step has received more attention. And we can see the evidence of this from a consistent stream of work that validates, verifies, and optimizes the prover. But the problem here is that even if our program is thoroughly verified with a perfect verification toolchain, the program can only be as correct as the specification. So what about the completeness of the specification? And in order to show the potential incompleteness problem in the specification, we here provide a motivation example. So the left part is the source code, and the right part is the specification for the source code. And the functionality of this add1 function here is that it will take a list of integers as input, and it will add 1 for every element in the list. And the specification specifies that in the returned list, every element will be added 1 compared with the precondition. So on first sight, there seems to be nothing wrong. However, if we mutate the source code a bit, we add a line of code that pops out 1 element after the adding 1 operation, the specification here will not be able to catch this mutation, and the verification is still going to pass. So in this case, we know that there is some blind spot that resides in the specification, so we can go ahead to locate the blind spot. And in this case, we fix the specification by adding an ensures that require the length of this stays the same after executing the function. And after the fix, the verification is going to fail. So we might think that why don't we just use this kind of approach to discover more blind spots in the code base? The problem is, in order to deploy mutation testing into the software verification context, we have at least 2 challenges. The first one is how do we determine the gap in the specification is by intention or by mistake? And the reason this is a problem is that not all blind spots discovered by mutation testing will be a mistake. For example, in this case, if we have a specification that requires for sorting algorithm, but it does not dictate specifically which sorting algorithm it is looking for. So imagine what will a programmer do under this case. And the fact is that the programmer will be free to use either merge sort, quick sort, or some other sorting algorithm, and all of these implementations will be reasonable. So our challenge here is that how do we determine the gap is intentional or mistaken? And in order to solve this challenge, another component from the development cycle came to our notice, and our solution here is to invite the test suite as a referee. And the idea is that specification, test suite, and code, these 3 parts are derived from the same set of requirements, but programmed with totally different mentalities. For example, they can be programmed in different language, asynchronously. They might have different evolution paths, or even they are probably developed by different teams. So this enables us to locate errors in one component by cross-comparing it with the other 2. So with this idea in mind, every time we find a mutant that passes verification, we will send it also to the test suite. And there will be in total 3 possibilities after the testing. In the first case, if the mutant verifies under the specification and passes the test suite, and the gap between the specification and the mutant is covered by the test suite, we will conclude that this gap is by design. And in the second case, if the mutant verifies under the specification and it passes the test suite, but the gap is not covered by the test suite, this will be an inconclusive gap, which means it requires us to further manually investigate into the true intention of this gap. In the third case, if the mutant verifies under the specification but fails to pass the test suite, we will conclude that this gap is mistaken. So with this matching scheme, we solve the first challenge. The next challenge is how do we produce mutants that are more likely to pass the verification? And in order to show the importance of solving this challenge, we first present an enumerative mutant generation approach, which we apply to the first case study in this work, the payment network. And the process of this enumerative way is that we will firstly pre-collect all the possible mutation locations in the code base. And in this case studies, we collected a total of 404 different locations. And then we will iteratively go over each mutation location following the generic mutation rules, which is listed in this table. And we will produce tab-preserving mutants. And here we set the upper bound to 3, which means we allow up to 3 different code locations to be combined together to construct a mutant. And the problem here is that in this case, we have about 400 different locations. But in the next case study, we have more than 6,000 different locations. So it is hard for us to even set the upper bound to 3. Not to mention that the actual search space is exponential. It is 2 to the power of n, where n is the number of all the possible mutation locations. So we need to find an approach that can produce mutants that are more likely to pass the verification. And in order to solve this challenge, and we are inspired by coverage-based fuzzing, our solution here is evolutionary mutant generation. So similar to the enumerative approach, the first step is to pre-collect all the potential mutation points in the code, and we will put all the collected points into a set of random mutants. And in the next step, we will initialize the seed pool with the original code without any mutations, and we will give it a high score to bootstrap the entire fuzzing process. And the seed pool here is consisted of all the registered seed by score. And in each of the fuzzing round, the mutant is consisted of the seed with the head score plus a random mutant. And we will send the mutant to the verification toolchain. And if it passes the verification, we will send it back to the matching scheme we developed to solve the first challenge. And if the mutant fails to pass the verification, we will send it to the feedback mechanism, where if a mutant is considered to be fit, it will be registered into the seed pool to become a new seed. And we also have a seed scheduling scheme here where we will award the parent seed if the new mutant is fitting, and we will penalize it otherwise. So as I have mentioned, we need to consider whether a mutant is fit in the feedback mechanism. So the reason we need to define a new fitness evaluation scheme here is that unlike code coverage-based fuzzing, where we can directly measure the code coverage, it is hard for us to directly measure the specification coverage. So we hope to use this scheme to better approximate the specification coverage. So our fitness evaluation scheme here is defined as mutant will be considered to be fit if they reduce verification errors compared with the seed mutant, or they uncover previously unknown errors. So with that, we solved the second challenge. And for the result part, we confirmed 13 cases on the first case study, the payment network, and 21 cases on S2N TLS, which is the second case study. And in order to better illustrate the result, here is a confirmed case on the first case study. So remember that TPN is a blockchain-based payment banking system. So this function eplog will be executed at the end of each transaction. And at the bottom of this function, there is a variable called sequence number, and it will be increased by 1 in order to prevent replay attack. And the problem here is that the specification for this variable sequence number is missing. So when we mutate the constant value here from 1 to 0, this mutant passes the verification. And at the same time, there's a line of code in a unit test that monitors that the value of sequence number will be increased by 1 by the end of the execution. So in this case, it matches the pattern where the mutant passes the verification but fails the test width. So based on our matching scheme, we confirm this to be a mistaken case. So and then we can fix the specification. And in this case, we fix it by adding an ensures to guarantee that the value of sequence number will be increased by 1 by the end of the execution. So this is one confirmed case on one of the case study. Besides this case, for the other case studies, all the fixed pull requests, pull requests to fix the confirmed mistaken blind spots, and we also have some detailed analysis report, and we also have some detailed explanation on several specific cases. All this information can be found in our paper as well as the GitHub repo. So welcome to check our paper and the GitHub repo. And that concludes my talk. I'm happy to take any questions. Thank you.
All right. Do we have any questions?
Thank you for your talk, and I'm Hyung-Suk Khan from Georgia Tech. How long does it take to verify the contract with SPAC?
You mean like for each round of the verification?
Yeah.
That depends on which verification framework you are using. Like in our case, the first case study is pretty fast. It's like within 1 minute. And in the second case study, it's like a bit slower, about 5 minutes. Yeah.
Okay, thank you.
All right. Do we have any other questions? No? All right. So we should thank Rudy for our talk, and we'll move on to the next group.